Hello and welcome to this video on identifying whether a given set is a subspace. All right, so here we'll be given a vector space. Now remember, a vector space is a collection of vectors along with the operations of vector addition defined in some way, and we're going to use the typical vector addition here, standard operation, where you just add corresponding components together, and also the operation of scalar multiplication defined in some way. Again, in this video we're going to use the standard definition of scalar multiplication, where when you multiply a vector by a scalar, a vector in Rn by a scalar Euclidean space, you multiply every single component of that vector by the scalar. And so we're going to be given a vector space, right? So you got the set of vectors, vector addition is defined, scalar multiplication is defined, and then those 10 vector space axioms hold, right? You have closure under vector addition, closure under scalar multiplication, then it's commutative under vector addition, associative under vector addition. There is an element, a vector that is typically referred to as the zero vector. That's the additive identity. That's also in the set. Every element, every vector in the set has an additive inverse, right, or an opposite. It's associative under scalar multiplication. There's a scalar usually denoted by 1, the number 1, that is the scalar identity. And then it's distributive in two ways. Right? You have two distributive properties. One where you can distribute a scalar over a vector addition and get the same result. And then it's also distributive where you can distribute a vector over the scalar addition, right, and get the same thing. So you have the 10 vector space axioms hold. Well, suppose we're given a vector space and then a subset of that vector space, right? A collection of vectors from that space. And then we're asked, is this subset also a vector space? Well, a lot of properties are inherited from the larger vector space. If you have a collection of vectors from a vector space, you get basically all the properties are inherited except for the closure properties. All right. So that's what moves me on to the next slide here, and Subspace Criterion. So suppose W is a subset of, and we're just talking about Euclidean space here, so collections of vectors with n components where each component is a real number. And also this, like as I mentioned earlier, the standard definition for vector addition and scalar multiplication. So suppose W is a subset of Rn, then we would say that W is a subspace of Rn, or a subspace, if and only if the following three hold. 1, W is non-empty, meaning that W contains at least one vector from Rn. 2, we must show that W is closed under vector addition. Now remember what this means. This means if I take two vectors that are in W, add them together, their sum will also be in W. And 3, W is closed under scalar multiplication. So that's what this means again, is that if I take any vector in W, multiply it by a scalar, any scalar, and here the scalars will be real numbers. Other vector spaces might be defined over a different field, but we're gonna go over the real numbers here. So if I take any vector in W, multiply it by any scalar, any real number, that scalar multiple is also in W. Right. Now a little note I put up here by the W is non-empty note. another thing you could say about this W is non-empty, if W is non-empty, so say there's a vector V that's in W, and it's closed under addition and closed under scalar multiplication, then the zero vector would also have to be in W. Let's think about that, right? So think about it. If V, just any vector V is in W, then if it's closed under scalar multiplication, then -1 times V, or opposite of V, would also be in W. And then if it's closed under vector addition, V plus -V, which would be the zero vector, would also be in W. So that's why, if all three of these hold, then another way to state the top one, you'll see in some texts, they say one thing you need to check is the zero vector in W, right? To check to see if W is a subspace. All right, and one little note here before I get on to some examples. The set with just the zero vector and the space itself, the entirety of Rn, are considered subspaces of Rn. They satisfy all three of these properties. Right? Zero, this has the zero vector in it, right? So it's not empty. Take any two vectors in here, well, they're just 0 and 0. Add 0 and 0 together, you get 0. So it's that's also in here. That's closed under addition. And multiply 0 vector by any scalar, it's the 0 vector again, so it's closed under scalar multiplication, right? So the set with just the 0 vector is a subspace of really any vector space, but we're just talking about Euclidean space here, Rn. And of course, we mentioned earlier Rn is a vector space, so it is also a subset of itself, right? Every vector in Rn is also in Rn. So it definitely satisfies these three properties because it satisfies all 10 of the vector space axioms. So the set with just the zero vector and the space itself are considered subspaces of Rn, but these are the easy ones, right? They call these the trivial subspaces. We're going to see examples of some non-trivial subspaces or proper subspaces in the coming pages. All right, so I got to check these three things. All right, so here are some examples. Now I'm just going to start off with some ones we can actually visualize. Some vector spaces we can actually picture, and that would be R2 and R3. I guess R1 as well, but R1 would just be the number line. Not really too much interesting going on there. The only subspaces of R1 would be the vector with just 0 in it, and then also the entire real number line. So the R1 itself, just the trivial subspaces. So I'm going to move up to and start off with examples from R2 and R3, pardon me. All right, so here's some examples of subspaces of R2. Now R2 is the the XY plane that you're used to probably from algebra class, really a lot of classes you've taken. So as I mentioned before, one example of a subspace of R2 would be just the set with the zero vector in it. And if you're thinking about the space of R2, that's just the origin, right? The zero vector basically is just the point 0, 0. So that's a subspace. It satisfies all three properties. It's non-empty, closed under vector addition, closed under scalar multiplication. W equals the span of any non-zero vector. All right. Now, when I say span of a vector, or the span of a set of vectors, remember that's just any linear combination of those vectors. So when I say the span of just one vector, the span of just one vector is simply all the scalar multiples of that vector. So 0 times this, 1 times this, a half times this, 5 times this, -8 times this, whatever. All those vectors, any scalar multiple of this vector belongs to the W, belongs to the span of it. And if you think about that in terms of R2, and I'll show you a picture of this in a minute, when you talk about the span of just a single vector in R2, that's really just describing a line. All the points at the ends of the vectors will kind of form a line that goes through the origin. And then the last type of subspace you're going to see for R2 is the span of any two vectors Oops, sorry, let me put that back down here. My apologies. It's my first time using this. The span of any two vectors that aren't scalar multiples of each other, so two independent vectors, you might have heard the word independent before. These are two, so again, this is the span of these two vectors. So any linear combination of these two vectors, so 3 of this one plus 5 of this one, 7 of that one minus 3 of that one, whatever. All these linear combinations of these vectors belong to this span, belong to W. And what you're going to see is that if you're looking at the span of two vectors that aren't multiples of each other, that aren't scalar multiples, that constitutes the entirety of R2, the entire plane. All right, so you got your trivial, which is just a zero vector, and R2 itself, and then you have these non-trivial subspaces, which are lines to the origin. All right, so like I said, I have some pictures of these. All right, so the first of these is here's just the zero vector, 0, 0 in R2. So here's x1 axis, the x2 axis, right? Or xy, if you want to call them x and y. And the zero vector is simply this point, right? The origin, and that's it. There's a subspace of the entire plane. Okay, very simple. Another example in R2. How about just the span of vector 1, 2? Now this isn't it. All right, I'm going to draw more on this, and I'll also go to a website to show you maybe a better visualization of this. But again, here's R2, right? You got your x1 axis, your x2 axis, or xy if you want to call them that. Here's vector 1, 2, right? Drawn from the origin. You got 1 to the right, 2 up. There's vector 1, 2. Now the span of vector 1, 2 is any linear combination of this, right? Basically any scalar multiple of this. So here's 1 times 1, 2 ends there. 2 times 1, 2 would be this vector here, ending there. 3 times 1, 2 would be this vector here, ending there. Negative 1 times 1, 2 would be this way, ending there. Negative 2 times 1, 2 would be that vector, ending there. And then you could do, half of it, 1.5 of it, 2.5 of it, negative half, negative 1.5 of it. And do you see how all the scalar multiples of that vector, basically the span of that vector, takes you to points that form a line through the origin, as I mentioned on the previous couple pages ago. All right, this is just a line through the origin. So really any line through the origin on the xy plane or x1, x2 plane in R2, right? This is R2 here. Any line through the origin you could say is representative of a subspace of R2. All right. And think about it, right? Again, you take the zero vectors in there. First of all, it's non-empty. 1, 2 is in here. And then you take any multiple of 1, 2, add it to any other multiple of 1, 2, and you get another multiple of 1, 2. So it's closed under vector addition. And then you take a multiple of 1, 2, multiply it by another scalar, and you get another multiple of 1, 2. So it's closed under scalar multiplication, right? So you got all three properties holding. This picture is the picture of the span of 1, 2. This is a subspace of R2. All right, and then as I mentioned, oh yeah, and let me show you I have a website brought up here. This is called Geogebra. I have the 2D and 3D up here. This is the 2D version because I want to share. Here's vector 1, 2 again. All right, and then here's the line, starting from the origin and containing all multiples of vector 1, 2, and it's the same picture I drew on the earlier page, but that is representing a subspace of R2. Okay, let me just turn these off now. All right. Okay, so back to my pages, and the third type of subspace of R2 I mentioned was this, right? Here's two vectors, 4, 2, and 2, 5, right? And I've drawn them here. There's 4, 2, and the vector 2, 5, one in like fuchsia and one in blue. And now this isn't the span, this is just the two vectors itself. When I say the span of these two vectors, I'm talking about all linear combinations of these two. All right. So one, it's not empty, right? Because you got 4, 2 would be in there, 2, 5 is in there. It's not empty. And take a linear combination of these two, add it to another linear combination of these two, and you'll get a third linear combination of the two vectors. So it's closed under vector addition. And if you take a linear combination of these two, multiply it by a scalar, you get another linear combination of these two. So it's also closed under scalar multiplication. All right. So now let's see how this would actually be the entire R2. Well, you've probably seen before that R2 is the span of 1, 0, and 0, 1. Right? Here's 1, 0, right? This vector here. And here's 0, 1, right? Just 1 unit right of the origin, going 1 unit up. And every vector in R2 can be written as a linear combination of 0, 1, 0, and 0, 1, those unit vectors. You've probably seen that already. And if I put up a bunch of 1, 0s and 0, 1s, I get the grid, right? You see how this grid here is made up of a bunch of 1, 0s and 0, 1s, right? Every single little square is kind of made up of these vectors. So I get this grid. Well, you can get another grid using these vectors here, right? Using 4, 2, and 2, 5, and you'll see the grid go over the entire plane. So I could get to any vector, I could get to any point I want on the plane using these two vectors. All right, so like I said, what I'm going to do is draw up a bunch of these, right? So here's a 4, 2. That's right 4 up 2. Here's another 4, 2, right? 4 up 2, right? Here's another 4, 2. And then right 4 up 2, and then here's another 4, 2. This is awful. Let me do this in red now. This will be better. And then right 4 up 2. Here's another 4, 2. And then so these are all like positive multiples of 4, 2. But then I could look at the negative multiples of 4, 2. So negative 4, negative 2. So left 4, down 2. There's negative 4, there's negative 1 times 4, 2. Then negative 2 times 4, 2, and so on. And then I do the same for the blues. All right, this is 2, 5. So right 2 up 5. Right 2 up. Here's another 2, 5. And then going backwards, there's a negative 1 times 2, 5. And can you see the grid here? Right, I get a grid if I think of this as instead of the vertical y-axis, I think of this line as an axis and this red line as an axis, and I get a grid forming. Right, so 4, 2, right? So right 4, 2. And I mean, I just put in one little square of the grid, but here's one part of the grid, and then there'd be another part of the grid over here. But this is just using the vectors 4, 2, and 2, 5 only, right? And I could get anywhere. If I took like half of 4, 2 plus half of 2, 5, I'd get up here somewhere. If I want to get up here, I could take so many 4, 2s plus so many 4, 2s plus so many 2, 5s running parallel to these lines, and I could get anywhere I wanted using just linear combinations of these two vectors. So you see how this is, it makes up the entire plane, right? So the span of this is R2. R2 is a subspace of itself. Any vector space is a subspace of itself. All right. And again, back to the website. Here's 4, 2 again. Here's 2, 5, like I mentioned. And just put the lines with those in. Those would be like the new axes, right? Like I mentioned, like this would be a new axis. This would be a new axis. And then to get to any point on the plane, I would go so many U's, so many 4 2's down this axis, and then so many W's or so many 2 5's up this line, and then see where they meet, and I could get to anywhere on the plane that way. All right, so the span of those two vectors is the entire plane, is the entire space R2. Okay, so those were some examples of subspaces in R2. Here are some examples. I'll just go one more up because there's only one more I can really visualize, right? R3 is three-dimensional space. You have a x, y, z axis, or x1, x2, x3. I can't visualize, I can't show you what R4 or R5 or R6 look like. All right, so there are subspaces of those, sure, but I can't really picture them, right? The way we have in our physical world. All right, so R3, that's three-dimensional space. Here's some examples of subspaces of R3. Now I mentioned earlier, remember the set with just the 0 vector, right, or 0, 0, 0, that's one of those trivial subspaces. That's always a subspace of any vector space, the set with just the 0 vector in it. And also R3 itself, number 4 here, right, which would be the span of 3 vectors that don't fall on the same plane. 3 vectors that are, now any 2 vectors can form a plane, but then the third one doesn't fall on that same plane. All right, so U and V form a plane. The span of U and V would form a plane, but then make sure this other vector W isn't on that plane. And if you have that case, then the span of 3 vectors like that would form all of 3D space, R3. Then you have a couple, the non-trivial or proper subspaces. If you have the span of a vector, some non-zero vector in R3, so basically any multiple of a vector in R3, you get a subspace, right? It satisfies all 3 properties, is non-empty, closed under vector addition, closed under scalar multiplication. And the points that those end at would actually end up forming a line containing the origin in 3D space. And also the span of any 2 vectors that aren't multiples of each other, that aren't scalar multiples, and that are non-zero. You take the span or any, the set of all linear combinations of this U and V here, you're going to get a plane, right? A plane containing the origin. That's again, especially has to contain the origin, right? It has to contain the 0 vector, the origin, to be considered a subspace. Satisfy that all 3 properties. All right. So like I said, I can picture these. Right? I drew a couple, but it'll be a lot easier to show you on a website. I found a Geogebra.org also has a 3D calculator, which I'll show you in a second. All right, so this is usually, because it's very hard to picture 3D images on 2D space. You have to draw. This is like my x-axis, or I'm sorry, my y-axis. My x-axis is the one that's on the 45-degree angle here. x1, then x2, and then x3 going straight up and down, or you could say x, y, z if you wish. And you got positives for x1 coming out of the page, negatives going in the back. Usually these are dashed. I think I dashed them in my future drawings. I apologize, I didn't dash them. Usually the negative sides of the axes are dashed. Then I have the positive y-axis or positive x2, and then negatives over here, and then positive z or positive x3, and then negatives down here. Now this subset of R3 with just the 0 vector, 0, 0, 0, again, is just a single point. Just that point there, the origin, 0, 0, 0, where all 3 axes meet. And that is a subspace of R3. It satisfies all 3 properties. All right. It's non-empty, closed under addition, closed under scalar multiplication. All right. And here's let me show you the GeoGebra 3D calculator up here, right there. I've just got point A, in black where all three axes meet. They have a green axis, a red axis, and a blue axis for like x1, x2, x3. And that's it, just that point with, point A there, 0, 0, 0, is a subspace of R3. Okay, so back to my pages. I drew as best I could some vectors in R3. I'm not the greatest artist. So here's an example of a vector in R3. And again, this time I had the dashed parts dashed where there are negative values. All right, so again, you have x1 axis, x2 axis, x3 axis. So take the span of one vector, say 3, 5, 2. Now how I would graph that is, I go to 3 on the x1 axis, 5 on the x2 axis. You draw a parallelogram, right? Parallel little segments parallel to those axes. Takes me to this point here, and then 2 on the x3 axis. I go up 2 units to be in line with 2 parallel to the diagonal, this parallelogram here. Basically, you create a little box, right? You know how when you graph on the xy plane, you can draw a little rectangle. This is a rectangular prism I'm drawing here with a 3 by 5 base and a 2 height, right? 3 by 5 base and a 2 height. And the corner of that prism is the point I want to go to from the origin. So from the origin to the corner of that prism, that vector is the vector 3, 5, 2. And all the vectors that are multiples of this form the span of 3, 5, 2, which will just be a line through the origin, and it's satisfies all three properties: non-empty, closed under addition, closed under scalar multiplication. Again, I think it's easier to, instead of just seeing my single picture of a vector here, going back to the Geogebra 3D thing, I have this put up somewhere. There it is, 3, 5, 2. See, there's the vector 3, 5, 2. Spin this around a bit, you can see it like 3D coming off there. Right? It's 3 in the red direction, 5 in the green direction, 2 in the blue direction. Right? And you got there's the vector. And every vector that's a multiple of this will form a line, right? And there's this line with all the vectors that are multiples of 3, 5, 2, and that line going through the origin, hopefully you can see it, it forms a vector space, or which forms a vector space. Right, which and then because it's a subset of R3, it's a subspace of R3. All right, let me turn those off. All right, and then I have the last, next one here, not the last one, but my next picture again, just a very rough drawing. All right, I drew the x1 axis, x2 axis, x3 axis. The little dashed parts are where the negative values are on those axes. And I say, well, what about let W be the span of 4, 6, 5 and negative 2, 3, negative 4, right? Two vectors that aren't scalar multiples of each other, so they don't run in the same direction or opposite directions. So again, for 4, 6, 5, I went to 4 on the x1, 6 on x2, made a little parallelogram, and then 5 units up, and then there's that vector, right, from the origin out to that point, 4, 6, 5. And then for negative 2, 3, negative 4, again, I went to negative 2 on the x1 axis, 3 on the x2 axis. It's in yellow. You can barely make it out. That's probably a really bad color. And I made a little parallelogram with negative 2 and 3 on those axes. And then from the corner of that parallelogram down 4 units and to this point here. And there's this vector 2, 3, negative 4. And these two vectors, again, will form like a grid, a plane. If I extended this to make a line and extended the other vector to make a line, those would be like two axes of a plane, like the xy plane. And you could get to any point on that plane by taking any linear combination of those two vectors. So the span of these two vectors form a plane. And it's a lot easier to see on a website. All right, so I got these plugged in already. Here's 4, 6, 5, right? That blue vector that just popped up. Here's negative 2, 3, negative 4, that red vector that just popped up. And again, there it is down there, right? It's pointing down. And can you see how, like, I'll draw a picture of the plane here in a second. All right, and here's the plane that contains a plane containing the origin where every point on that plane can be gotten to by a linear combination of the red vector and the blue vector. All right, let me turn it this way so you can definitely see that every point on that plane is in line with those vectors there. See, those two vectors form a plane. Right, red, blue, right, like that. Nice little sheet. Okay. So, and then this plane containing the origin, right, is made up of, again, every linear combination of 4, 6, 5, and -2, -3, 3, -4. And that forms a subspace of R3. Right? It's closed. It's not empty. Closed under vector addition. Closed under scalar multiplication. All right, and then back to now. That's the last drawing I have because again, my 3D drawings aren't incredible. But you could also say that another subspace of R3 is R3 itself, right? The entire 3D space. And as long as you have three, you could take any three vectors that don't fall on the same plane. So like, 1, 0, 0, 1, and then, 1, 0, 0, 0, 1, 0, and 0, 0, 1, the three basic unit vectors, they might call them I hat, J hat, and K hat. Those three, the span of those three, make up the entire 3D space, right, R3, because every vector in R3 can be written as a linear combination of I, J, K, right, 1, 0, 0, 0, 1, 0, and 0, 0, 1. But you could find three other vectors that also do the same thing, all right, that you could make a little grid system, 3D grid system with three other vectors besides I, J, and K. Okay. All right, so got those examples out of the way, all right, just hopefully you see, at least in R2, hopefully you can now visualize in R2 and R3 some examples of subspaces of R2 and R3. Now let's actually go into, I got a bunch of examples here where I'm trying to now find, or determine, sorry, whether or not the set W is a subspace of the given vector space V, all right. So my first example, and this is every example from here on out. All right, my first example is, it's a set of all vectors, x1, x2, these are in R2. I got two components such that x2 equals 3x1. All right, so the second component is triple the first component. And of course, the vector space that this is a subset of is R2, right? All these vectors are vectors in R2. So, a lot of times I find that people have a hard time understanding what vectors would actually belong to W. So here are just some, right? Just some vectors. This isn't proving anything. Okay, I'm not doing this yet. I'm just trying to show some vectors that are in W. Let's see. Again, just read the description. The condition that needs to be met. It's got first component, second component, and the second component is triple the first component. So 1, 3 would be in there. 0, 0. We already, we want that to happen. Remember, we want the 0 vector to be in there. -2, -6. And so on, right? You could do this forever, right? This one doesn't have just a 0 vector, and it has infinitely many vectors, and I could do this all day long. So it's definitely not empty. All right, so 1, remember that first property, it's not empty. Check. 2, is it closed under vector addition? I'll just say closed under vector addition. Right? All right, so I don't know yet. All right, so this is where you have to, now you can't just take two examples. I can't just say, 1, 3 and -2, -6. When I add those together, I get -1, -3, which would also be in W, so it's closed under addition. You just giving me one example with some specific numbers doesn't prove anything. Specific examples do not prove general statements. So we have to go in general. I have to say, let's suppose, since I know it's not empty, we know there's some vectors in here. So I'm going to say let vector U, I'm just going to call them something, U equals, U1, U2. and another vector, say w with components w1 and w2. Let's say these belong to w. All right, I know, because I know it's not empty. I know there's some vectors in there, at least one. So let's say we have 2. All right. So I got these vectors that belong to w. Now remember what that means. All right. This is where the condition comes in. If u1, if u belongs to w, that means that u2 is equal to 3 times u1. And if this vector w, I said this general vector, belongs to w, then that means that w2 is 3 times w1. All right, now we look at their sum. And hopefully their sum is also in this set w, meaning that this condition will hold. All right, so let's look at u plus w. Now, as I mentioned earlier, we're using standard definitions for vector addition and scalar multiplication. So what would u plus w be? It would just be u1 plus w1 for the first component, and then u2 plus w2 for the second component. And the question is now, is this in w? So basically, do these components, would they satisfy this here? So the question is, does u2 plus w2 equal 3 times u1 plus w1? That's the question. If the answer to this is yes, then we're good. It's closed under addition. If the answer to this is no, then it's not closed under addition. And this is not a subspace of R2. Well, this is where we use our original facts, right? We said u and w were in set w here. So these two must hold. So, u2 plus w, since u and vector w belong to w, go to another page here. That means that u2 plus w2 must be equal to, well, u2, since u belongs to w, u2 is equal to 3u1. So I replace u2 with 3u1 plus, and then w2, same thing. Since w belongs to set w, w2 must be can be replaced with 3w1. And then look at these two. They both have a common factor of 3. I can factor the 3 out and get 3 times u1 plus w1. And look, that's exactly what we wanted to show. u2 plus w2, the second component of the sum, is equal to 3 times the first component of the sum. So the answer to that question is yes. And because it is, I'll put a little check mark here, this set is indeed closed under vector addition. All right, and then the last part, is the set closed under scalar multiplication? All right, I don't know yet, so I'm not going to put a check. Now I've already got vectors that I say belong to w, so I'm going to have just u again. All right, so suppose we have vector u and w. So there's a vector in w, and then that means that the second component is 3 times the first. All right, u2 is 3 times u1. And now I'm going to take any scalar. All right, I'm going to say r for a real number. Let r belong to one real numbers. Be any scalar. All right, and again, you can't just use a specific one. Right, one specific example doesn't prove a general statement. All right, we have to go general here. Use letters. Then we look at the scalar multiple, r times u. All right, is r times u in set w here? Well, what is r times u? R times u, right, would be ru1 for the first component and ru2 for the second component. And then the same thing as I asked before, does this belong to w? The question is, is the second component, ru2, equal to 3 times the first component? Right? Does it satisfy that condition from the set w? Well, since we've stated, since U is in W, right? Since vector U is in W, we know that U2 is equal to 3U1, and then I would just simply multiply both sides by R, and do a little associative property here, because 3 times R times U, you can rearrange stuff. These are all real numbers here. So yes, that does indeed happen. Any vector times a scale times any scale, any vector in the set W times any scalar would still be in W, right? So it's not closed. So it is closed. Sorry, under scalar multiplication. Therefore, since all three properties hold, W is a subspace of R2. All right. And since it's R2, I mean, you could even make a graph of vectors that satisfy this. Like I said, 1, 3, 0, 0, -2. If you put those up, though, if you were to put those up, remember how I said earlier, one of those subspace, and one example of a subspace of R2 was lines through the origin, right? 1, 3, 0, 0, -2, -6, 2, 6, 3, 9, blah, blah, blah. Any vector that belongs to this, any vector that satisfies this, you see would form a line through the origin on R2, as I mentioned before. Okay, so that one was a subspace. Got plenty more. All right, so how about this one? All right, so here I have a set W. So all these vectors in R2, right? It's got two components, such that the product of both components must be 0. Now, if the product of both components must be 0, that means at least one of the components has to be 0, right? So here are, again, I'm not proving anything yet, but I'm just can I think of some vectors in W? So obviously the 0 vector would be in there, which is great. All right, we want that. But plenty of other ones too, right? Anything where the product of the components is 0. So 0 for the first component, 5 for the second component. -8 for the first component, 0 as long as one of the components is 0, right? This tells me that at least one of the components has to be 0, and there's plenty of other ones, so it's definitely non-empty. Check. All right, it's definitely, this set W definitely has some vectors in it. All right, is it closed under addition? I'm just going to put addition. All right, there's add. Is it closed under addition? I don't know. All right. Now, you could probably already see just from my examples up here. Now, remember I said earlier, to prove that a general statement is true, you need general stuff. You need variables. You need letters. You can't just give me one example. But to prove that a general statement is false, isn't happening, you can show me just one counter example. And I'm going to say no on this one, and here's why. I can see it right now. Look at these examples. 0, 5. This is in W. -8, 0. This is in W. But their sum, right, when I look at their sum, it'd be -8, 5. This would not belong to W since, -8 times 5 is not 0, right? It doesn't satisfy the condition of the set. So W is not closed under vector addition. All right. Now it would be closed under scalar multiplication, but that doesn't matter, right? Because if one of these is 0, like it has to be, and then I multiply it by a scalar, that component that was 0 before will still be 0. So it is closed under scalar multiplication, but it's not closed under vector addition. So W is not a subspace of R2. All right, and let's look at some, and let's graph some of these too. Again, because it's R2, I can actually picture this. It's R2, right? 0, 0's there. 0, 5. Anything with 0, 0, 10, negative 3, 0. I'm sorry, 0, negative 3. But it's like, hey, you might be thinking, hey, that's a line through the origin. Didn't you say that was a subspace? Yeah, but look at this too. You got negative 8, 0, 3, 0, 10, 0, like all these too. So it's not just a single line through an origin. I get this cross thing, this X shape. And you're not able to reach points out here either. So it's not like R2 or anything. So it's two lines through the origin at the same time. That's not one of those examples I threw up earlier of a subspace of R2. All right. Because again, if I were to add, right, this guy and this guy, it'd be, take me to this point out here, which wouldn't satisfy that condition, right? Because the product of these components wouldn't be 0, right? All right. All right, next one. So I got a few for R2 and a few for R3, and you just watch as many as you need to until you feel like you understand. All right, so this time W is another subset of R2, right? Vectors in R2 with 2 components. And here's the condition that needs to be met now. 4 times x1 plus 3 times x2 must be equal to 0, right? I guess another way you could say this too is that, say x2 needs to be negative 4/3 times x1. Same thing, right? I'm just solving that equation for x2. So as I've been doing, right, can I think of, and you should be doing this too when you're given a set, any set, can you think of some vectors, if there are any, that are in this set? Well, this one has the 0 vector again, very nice, right? Because 4 times 0 plus 3 times 0 would be 0. So it's not empty, wonderful. Some other ones, if x1 was 6, and this would be negative 8, and I'm just using this relationship here, it's the same thing, right? That's in there, and if x1 was negative 9, this would be 12, right? And so, I mean, there's loads of them, right? You can just plug in values to this or plug in values up there. Find vectors that actually belong to this set, right? As long as the second component is, negative 4/3 times the first component, or 4 times the first component plus 3 times the second component is 0, and that's happening for these 3 that I put up here. All right, so it's definitely non-empty. Got that. Check. Is it closed under vector addition? All right. Well, again, you can think of a few examples if you want, like if I added these 2 together, I'd just get 6, negative 8, which is in W. If I added these 2 together, I'd get negative 3 and then 4. Is that in there? Yeah. Negative 3, 4 would be in there. So, and then if I add these together, I get, negative 12, 16. Is that in there? Well, yeah, it is. So that's not a proof, right? I haven't proved anything. But just after, just going over a couple examples of sums and seeing that when I add 2 vectors in W, I get another vector in W, it feels like this should be closed under addition, but we have to prove it. It's a general statement about all the vectors, so I have to use some letters, variables, to represent, general statements. So again, I'm going to use, I'll say U and V this time, right? So U equals, U1, U2, and V equals V1, V2. Right? Suppose these belong to W. Now, what does that mean? That means that, so U belongs to W, meaning that 4 times U1 plus 3 times U2, should be equal to 0. And since V, this other general vector V, belongs to W, it should satisfy this condition as well. So 4 times V1 plus 3 times V2 should be equal to 0. All right. Now look at their sum. Again, U plus V using standard definition of vector addition here. That'd be u1 plus v1 for the first component, u2 plus v2 for the second component. And then the big question is this. Is 4 times the first component, right, 4 times the quantity u1 plus v1, plus 3 times the second component, right, 3 times the quantity u2 plus v2, is that equal to 0? Because if it is, then our sum is in W and it's closed under vector addition. If this is not 0, then it's not closed under vector addition. And we should be able to find an example, a counter example, right? Well, let's take a look at this. All right, so let's look at the expression 4 times u1 plus v1 plus 3 times u2 plus v2. Let's look at that expression. Now, if I distribute, all right, let's mess with this a bit. If I were to distribute the 4 and the 3, we'd have 4 times u1 plus 4 times v1 plus 3 times u2 plus 3 times v2. And then I could rearrange terms, right? This is just a big sum. And the reason I'm going to rearrange the terms is I'm going to rearrange the terms so I have the u's together and the v terms together. And you'll see why. This is 4u1 plus 3u2 plus, and then 4v1 plus 3v2. And the reason I did that is because, look, this expression on the left here that I started with, we know that u is in W and v is in W. So remember, if u is in W, then this is 0, this 4u1 plus 3u2. And since v is in W, this is 0, the 4v1 plus 3v2. And we're getting 0, which is what I wanted, right? 4 times the first component of the sum plus 3 times the second component of the sum is equal to 0. So the sum actually satisfies this condition, so the sum actually belongs to W. Check on that. It is closed under vector addition. So now I must check if it's closed under scalar multiplication. So again, I'm just going to put mult here, but just know it's by a scalar. And again, you can't just use... Now you can start off with some examples if you wish. You know, if I'm like, hey, take this guy here, negative 3, 4. Let's say I multiplied that by 5. Then I'd get negative 15, 20. Would this be in W? If I multiply that by 5, you know? Well, yeah, this satisfies this. You know, multiply this one by a half. You know, would negative 9 halves and then 6 be in it? Yeah, it would. You know, you can check it. So it seems to me, after just looking at a couple examples, that this set is indeed closed under scalar multiplication. So I have u and v already, right? So I have some vectors I already called R and W, so that means that, you know, 4u1 plus 3u2 equals 0. I'm going to let R again belong to the reals, so I'm just going to let that be some any scalar. And then we're looking at R times u, right? When I take this vector u from W, multiply it by R, is it also in W? Is RU in W? So that'd be RU1, RU2 for the components. And then again, the big question is 4 times RU1 plus 3 times RU2 equal to 0, right? Is 4 times the first component plus 3 times the second component equal to 0. Well, look at this expression here, 4 times RU1 plus and then 3 times RU2. They both have R in it, right? Again, I'm not saying it's equal to 0 yet. I don't know that it's equal to 0. I'm asking, is it equal to 0? They both have R in it. You can factor that out. Then you have 4 times the quantity 4u1 plus 3u2. And then, hey, didn't you say that u was in W? So 4u1 plus 3u2 must be 0. So this is R times 0, which is 0. Yes. This 4 times the first component of the scalar multiple plus 3 times the second component of the scalar multiple is indeed equal to 0. So the scalar multiple does belong to W. So check on that. So all three properties hold. This set is non-empty. It's closed under vector addition, closed under scalar multiplication. So W is a subspace of R2. And again, since it's R2, you could also talk about making a little, do a little graphing. All right, here's a little XY plane or X1, X2 plane. You got 0, 0. You'd have 6, -8, -9, 12. Right. Again, I just know it's going to be a line. Look at the equation here. This is a line through the origin. All these vectors, -3, 4. 12, 12, 6, 12, -16. Again, you get this line through the origin. As I mentioned earlier, when the vectors form this line through the origin in R2, then you have a subspace of R2. All right. Okay. Next one. All right. Still in R2. I got a couple more in R2, a few more in R2, and then a bunch in R3. Again, you don't have to watch all these if you don't want to. Just as much as you need to understand what's going on. All right. So here, W is the set of all vectors in R2 again, such that the second component is the first component plus 3. So just as before, can you, before I even go into proving anything, can you think of vectors in the set? Because that'd be nice to know. So some vectors in some vectors in W. Well, it's not empty, right? Because this is basically saying the second component just needs to be 3 more than the first component. So 0, 3 is in there. Cool. 1, 4. -3, 0, and so on, right? As long as the second component is 3 more than the first component, it's in W, right? So it's not empty. But one thing about this non-emptiness, right? Remember I mentioned earlier that if you satisfy all 3 properties, then the 0 vector should be in there. Would the 0 vector be in this? So right away I'm seeing that this is not going to be a subspace, but get rid of this pink one. Okay, but uh, 0, 0 markers would not belong to W, right? Because this does not satisfy the condition. The second component is not 3 more than the first component. So right away I can see that this is not going to be a subspace, all right? But you can say, okay, non-empty, say you don't recognize the 0, 0 thing. It's not empty, sure, there's vectors in this. Is it closed under addition? Well, let's test it out. If I were to add 0, 3 and 1, 4, that would give me 2, 7, right? 0, 3, and I can tell you right now that that's not going to be in W, right? 0, 3 plus 1, 4, right? Here are vectors that are in W, but their sum, 1, 7, not 2, 7. Their sum, 1, 7, this is not in W. All right, this is not in W since 7 is not equal to 1 plus 3. Right? It doesn't satisfy the condition. The same thing, so it's not closed under vector addition. So therefore, W is not a subspace of R2. It's also not closed under scalar multiplication. And again, if you want to show something, a general statement is false, it's not closed. You just need one example. If I were to take 1, 4, or even 0, 3, take 0, 3 and multiply it by 5, then you'd have 0, 15. Would 0, 15 belong to this? No, it wouldn't, right? Because 15 is not 3 more than 0, right? But all you need to figure out is, as long as one of these properties fails, W is not a subspace of R2. Okay. All right, and again, if you were to graph, do a little graph, because it is R2, you can picture stuff. 0, 3 takes you to here, this point. 1, 4 take you to this point here. Negative 3, 0 would take you to this point here. And the points that they form would be a line, sure, right? Now this is a linear equation still, all the variables are to the first power. But all the points that the vectors take you to would not be on a line through the origin, but they'd be on, some line not on the origin, right? Remember I said earlier, right, a line not on the origin, not containing origin. And I said earlier, if you're in R2, if the vectors are forming, if the points at the ends of the vectors are forming a line, the only way you're going to be forming a subspace of R2 is if that line contains the origin. All right. So great. So not a subspace. Here's another one. So again, some vectors with, now this one there's no condition, but you can see the condition. You see how the first component, well, basically x1 is real, right? So you see how this component is just negative 3 times this component, right? And there are vectors in R2. Right? So again, let's just think of what are some vectors in this set before I go proving anything. Can you even think of vectors in this set? Well, 0, 0 would be in here, right? Because, this is 0 and that's negative 3 times 0. 1 here, negative 3 there, right? Negative 2 here, 6 there, whatever, right? As long as that top component is negative 3 times the bottom component. Right? So it's not empty. Great. I have found some vectors in W. Then is it closed under addition? Right? Is it closed under vector addition? Again, this isn't proving anything, but I'm just going to, when I add these two, I get negative 3, 1, which would be in there. When I add these two, I get 3, negative 1. Is this in W? Yes, it would be. When I add these two, I'd get 9, negative 3. Would 9, negative 3 be in there? Yeah, the top component is negative 3 times the bottom component. So it looks like, just based on a couple examples, that's not a proof, but it looks like it is closed under vector addition. All right, so as with all the other ones that I actually had to prove it for, right? When it seems like it is true, you have to prove it. All right, so again, I'm going to have u and v. Right, so let's say u equals, I'm going to say negative 3 u1, u1 belong to w, and v equals negative 3 v1, v1. Right, these both belong to w, right? Because they have the same form that the vectors in W have, right? The top component is negative 3 times the bottom component, right, in both of these. Look at their sum, u plus v. And again, we're doing standard vector addition, so negative 3u1 plus negative 3v1. Really, you could just write minus 3v1. And then u1 plus v1. And then the question is, does this sum have the same form that all the vectors in W do? Right? Is the top component negative 3 times the bottom component? Well, yeah. Look at the top component. They both have a common factor of negative 3. I pull that out, and then I have negative 3 times u1 plus v1, and then the bottom component is just u1 plus v1. So you see how it is in that same form, right? The top component is negative 3 times the bottom component. So this belongs to W. Yes, it is closed under vector addition. All right, and then is it closed under scalar multiplication? I'll put mult, just know it's scalar multiples, right? Now, I suspect that it is because, again, you take any of these vectors up here that are in W. Let's say I take this one. Let's multiply this by 4. You'd get 12, negative 4. Is this in this set? Yes, it is. The top component is negative 3 times the bottom component. Take this, multiply this one by negative 3/4 or something. All right, I'll do something simpler. All right, multiply this one by negative 3. That'd be a negative 18, and then positive 6. Is this one in W? Yeah, because the top component is negative 3 times the bottom component. So it looks to me, after looking at just a couple examples, it looks as though the set is closed under scalar multiplication. All right, so again, I've got U here. Let's use this guy, and then let's do a scalar. Let R be a scalar, right? Some real number. And then we're looking at R times U. Is R times U also in W? Does it take on this same form where the top component is negative 3 times the bottom component? All right, so that would be R times negative 3U1, R times U1. And yeah, you can, because when these are all real numbers here, U1 and R are both real numbers. You can, the real numbers, they're a field with multiplication and addition. You can move the parentheses around, move the factors around. You could actually write this as negative 3 times RU1 if you wished, right? These would be the same product. And then the bottom component is still this R times U1. And this indeed has the same form as every vector in W, where the top component is negative 3 times the bottom component. So this vector RU, a scalar times U, does indeed belong to W. It is closed under scalar multiplication. So all three properties hold. W is indeed a subspace of R2. Wonderful. And again, if you were to look at graphs or put these vectors on a graph, the points at the ends of the vectors would actually form a line going through the origin again. All right, another example of a subspace of R2. All right, I've got one more here for R2 and then several for R3, and we'll be done. All right, so here, a set of all vectors in R2, right, two components, such that the first component, x1, is non-negative, right, greater than or equal to 0. The second component is also non-negative, greater than or equal to 0. So again, before I go into proving anything, can you name some vectors in W? Well, 0, 0 would be in there, great. Right, because the top component and bottom component are both non-negative. 1, 5, negative, not negative, 6, 6, 3, whatever, right? As long as the top component and bottom component aren't negative, it's a vector in W. Okay, so it is non-empty. Check. Is it closed under vector addition? Well, yes. All right, I'm just going to state that here. If you take any, remember how each component is not negative? When you add them together, all right, that'd be 7, 8. You add those two together, you get 13, 11. When you add a number that's not negative with another number that's not negative, you're getting another number that's not negative, right? So if I had, x1, x2, and y1, y2, and added them up to get x1 plus y1, y1 plus y2, and all those x1, y1, x2, y2 were not negative, the resulting sum would be not negative. So it is closed under addition. The only reason I'm rushing this is because I know the third one fails. Is it closed under scalar multiplication? So remember, this is take any vector in W, multiply it by any scalar, any real number. So not positive necessarily. So what if I were to take 6, 3 there? All right, this is in W. All right, this is a vector in W, and I multiply it by the scalar, negative 5. That's a scalar. All right. Well, that gives me negative 30, negative 15, and this is not in W because negative 30 is less than 0, negative 15 is less than 0, because both conditions, if one of the components is negative, it doesn't belong to W. Right? And both of these components are negative, so it doesn't belong to W. So it's not closed under scalar multiplication. Right? And if you were doing the graphing thing, You know, look at the points at the ends of the vectors. What kind of shape do they form? Yeah, you got 0, 0. And look at this. You know, you got 1, 5, do. You know, you got 6, 3, do. You know, basically, you're pointing to every single point up here. You're pointing to every point in the first quadrant. Right? You could hit everything up there in just the first quadrant, though. As soon as you multiply by a negative, you're down here and you're not in that space anymore. Right? So yeah, it's not one of those subspaces of R2 that I mentioned earlier, right? Where it's just, you know, the zero vector alone, or a line going through the origin, or R2 itself. Those are the only three kinds of subspaces under the standard definition for addition and multiplication. All right, so W is not a subspace of R2. Great. All right, now into R3, which again, I won't be able to visualize so well. I'm not going to draw them like I was with R2. R2 is real easy to draw. It's just XY plane stuff. R3, you can draw it, but it's, you know, harder to see, and, you know, there's no depth on a piece of paper. Right? There's length and width, but there's no depth, no height. All right. So here again, I've got all these vectors that, you know, three components, where the first component is some number, x1. The second component is always 0. Third component is just the first component plus 1. All right, so as I said before I even prove anything, I like to think of what are some vectors that would be in W. Well, 0, 0, 1 would be. Now notice that as with a similar problem earlier in R2, this plus 1 throws some things off. You know, the 0 vector will not be in this set because 0, 0, 0 doesn't look like this. You know, if I have the first component is 0, the third component has to be 1. So I know it's not going to be right away, just because of that, it's not going to be a subspace of R3. But here's another one, you know, 1, 0, 2. You know, -5, 0, -4. Right? All these are in W. All right, so it is non-empty. Okay, it's non-empty. It's got some vectors in it. Check. But, right? As mentioned earlier, you know, the 0 vector is not in this set. Right? Is not in W. So that means one of these other two has to fail. All right. It's either not closed under addition or not closed under scalar multiplication. And really, it's both. Look at the addition. Right. I'll just take these two vectors here. Take 1, 0, 2. That's in W, right? And add it to -5, 0, -4. That's also in W, but their sum, which would be -4, 0, -2. This is not in W. The reason is -2 is not -4 plus 1. Right? If this were in W, it should be -3 for the third component. Right? The third component needs to be only 1 more than the first component. So it's not closed under addition. You could also check that it's not closed under scalar multiplication, but all you need to do is show that one property doesn't hold to show that it's not a subspace, right? So W, this is not a subspace of R3. And going back to those examples earlier in the video, remember I said the types of subspaces for R3 are just a 0 vector, a line, the points of the vectors will make a line, the points at the ends of the vectors will make a line going through the origin, or a plane containing the origin, or the entirety of R3. You would see here that this would not even be, well, this would be a line. All the points on the ends of these vectors would form a line, just not a line containing the origin. All right, so we don't get our subspace that we'd like. All right, here's yet another one. All right, so W equals, and I got a few simpler ones because again I'm not going to really draw pictures. Just, you know, vectors from R3. There's a number x1 for the first component, a number x2 for the second component, and then always 0 for the third component. All right, so again, what are some vectors in W? Now this time, the 0 vector would be in W, right? But then, lots of other stuff. 1, 2, 0, -5, 18, 0, pi, square root of 2, 0, right? There any real number for the first two components, and then 0 for the third component, right? So it's definitely non-empty, and the 0 vector is in there, right? Check. Is it closed under vector addition? All right, so I'm just gonna speak it out loud this time, all right? I guess I'll do it. Here's a vector that would belong to W. Here's another vector that would belong to W, say with y1, y2, and then 0 for the third component. Both of these would belong to W, where x1, x2, y1, y2 are real. If I add those up, you got x1 plus y1 in the first component, x2 plus y2 in the second component, and then 0 plus 0, which is still 0 in the third component. And this looks exactly like these vectors here, right? There's a real number, right? A real number, and then 0. So this belongs to W, and yes, it's closed under vector addition. And then take a scalar. Again, take, say, r times a vector from there, x1, x2, 0. And this would be rx1, rx2, and then anything times 0 is 0. So it still has that same look, right? There's a real number, and then 0. So yeah, it's closed under scalar multiplication. Great. So yes, W is a subspace of R3. Right. And what you'd see is, if you were to look at a graph of this stuff, if you were to make a three-dimensional picture, this is actually a plane in R3. This is actually just the xy plane, right, whereas z is always 0, or the x1, x2 plane. And it's a plane containing the origin. All right, so again, one of those examples of subspaces of R3 I mentioned earlier. Yeah. All right, and finally, last example. W equals, again, similar look, but this time the third component's always 5. So right away, you can probably tell this won't be a subspace of R3 because, the 0 vector will not be in it. But let me just put up some examples right here. Again, here are some vectors in W. You'd have 0, 0, 5. Right? Again, some real number, then 5. 1, -8, 5, blah, 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 right? Lots of stuff. So it is not empty. Right? You can think of some vectors in it, but again, there's that caveat that the 0 vector is not in W because it doesn't have a third component of 5. So right away, I mean, really you can stop there and say that W is not a subspace of R3, right? Because if the 0 vector is not in W, that just means that one of the other two properties fails, which you're going to see right now, right? Is it closed under vector addition? No. Look at these two I just threw up here. Take 0, 0, 5, that's in W, plus take 1, -8, 5, that's in W, and add them together, you get 1, -8, 5, 10, 10, which would not be in W because, 10 is not 5, right? The third component is not 5. It does not look like the vectors in W should. So not closed under vector addition. Also definitely not closed under scalar multiplication, right? If I took here this vector in W, multiplied it by 3, it'd be 0, 0, 15. The third component would not be 5. And in order to be in W, the third component has to be 5. But as long as one of these fails, you know that W is not a subspace of R3, right? And there you go. Okay. All right, so that's it for today. Well, not today, but that's it for this video. on determining on subspaces and just of Euclidean spaces of R2, R3, and higher, right? I didn't do any examples of any higher spaces, but you can still do this. It's still the same concept. You're still checking for the same three things. Is the subset W, is it non-empty? Is it closed under vector addition? Is it closed under scalar multiplication? And then check all those three things. And if the answer to any one of those is no, then it's not not a subspace. Okay. Yeah, so that's it for this video. Hope you enjoyed it. Hope you got a lot out of it. Again, you can skip around. You don't have to watch the whole thing. Just skip around to certain examples. Hopefully you get something out of it. And yeah, take care. Thank you for watching.